This video, we're going to talk more about the difference between analytic solutions and qualitative analysis, featuring October, who also likes to sleep during math lectures. We will not see my third cat right now because the third cat is still protecting the house from my other two cats, which means she will murder them. They are in isolation right now. So remember, to find an analytic solution, currently we only know how to do that with separable equations, right? We'd get all the variables on one side, we'd integrate both sides, we could find an analytic solution to a differential equation. And then we could plot those solutions. And that's really quite a lot of work and quite a lot of steps. But for qualitative analysis, right? Think about this thing that we couldn't solve. This is pretty simple, but we could generate a slope field pretty quickly. And from that slope field, we can very quickly identify, not exactly, but very closely, how we think these solutions might behave, right? And we like had this sort of thing. We like, okay, that's generally how the solutions are going to behave. We didn't have to solve a differential equation. We just had to graph something. We did it by hand, and it was pretty quick. Think of how quick it is for a computer. All right. So it's very powerful because a lot of times, sometimes we really might want to predict exact values, and we'll want maybe an analytical or a numerical method to do that. But a lot of times we just want to know what's going on because, again, think back to modeling. And this is one of the really exciting things about differential equations is the modeling. We can start with a very simple situation. Think of the fact that maybe think related to the heat equation, where the rate of change of heat transfer is going to be proportional to the difference in heat, which sounds kind of complicated, but all it's saying is if there's, two things, or maybe one thing with multiple parts, whatever, if there's two things that are different temperature, how are they going to change over time? Well, the bigger the difference in temperature, the faster those temperatures are going to change, right? If it's hot outside, cold inside, they're going to, probably inside's going to change more than outside, right? And that rate of change is going to depend on how hot it is outside, essentially, right? That difference. That's a very simple thing to start with. And then we can write that pretty easily in a differential equation. Solving that differential equation, much more complicated. But doing qualitative analysis, not as bad. So let's do some examples kind of showcasing this a little bit. We're going to consider two differential equations. All right, and again, I don't know how simple they are. This first one's pretty simple. dy dt is just going to be 4y times 1 minus y. And the second differential equation is going to be less simple. Dy dt equals e to the y squared over 10 times sine squared of y. And we are going to be able to do a ton with both of these, which is very exciting. So this first one, I could ask you to find an analytic solution. It's a separable equation. It's autonomous. All autonomous equations are separable because if there's no t, then you can always get the y's to one side by just dividing by the whole thing. But if we did that, essentially, if you do try to find an analytic solution, you're going to come across something that looks like this. 1 over 4y times 1 minus y dy equals the integral of dt, which if you remember Calc 2, you can solve. But if you remember Calc 2 well, you will remember that this is partial fraction decomposition, which may or may not be your favorite part of Calc 2. It is literally my least favorite part of Calc 2. Nobody likes partial fraction. That's probably not true. I'm sure somebody out there likes partial fraction decomposition, but it's not me. And so this is very tedious. We don't like doing this usually. Okay, but we can. We're over here, again, another autonomous differential equation, but when you separate it out, you're going to get, the integral of 1 over e to the y squared over 10 sine squared of y dy equals integral of dt. We do not want to do this. I don't think this is possible. In fact, I'm pretty sure it's not possible. At least not in terms of elementary functions. So this one is like a double sad face, right? Analytic solutions are not the be all end all. All right. That's maybe the biggest summary for this class I want you to think about is we're not here to solve differential equations by hand. We're here to talk about differential equations. We're here to talk about models. We're here to talk about qualitative analysis and numerical solutions and how differential equations behave. How do we set them up? How do we interpret them? That's the important thing here. Okay. We're kind of at a level of math, I think, where it becomes less important again to be able to solve everything by hand. So qualitative analysis, though, is extremely powerful right here. Like, let's look at this somewhat nasty differential equation. Let's look at B. We actually can answer quite a few things about B. For example, we could do some pretty powerful things by hand. I'm going to copy this to the next page to give us more room to write. All right, if I asked you, what are the equilibrium solutions? You could find that, depending on how well you remember your trig. This is one thing times something else. Whenever you have multiplication, remember equilibrium solutions are when the derivative equals 0. And remember, we can use that y dot notation. That means the rate of change of y with respect to t. Y dot is a derivative when time is the independent variable. Just reviewing some new notation here. It's when the derivative equals 0. Exponential functions never equal 0. So our equilibrium solutions are just going to be when this equals 0. We can solve that trigonometric equation, remembering back to our trig. And that's just going to be when sine is 0. Sine is the y coordinate on the unit circle. So sine is equal to 0 here. So the equilibrium solutions are going to be when y is equal to 0 plus pi times any constant, where k is some integer. So again, we don't usually write the 0 here, but we just found infinitely many equilibrium solutions with qualitative analysis. All right, we don't even need a slope field for this, but we could, right? We could start generating a slope field, and this is where I start to get really excited. There's just some really cool things that we can do here. We just found out, right, that every pi is an equilibrium solution. So there's an equilibrium solution here at 0. There's an equilibrium solution here at y equals pi. Equilibrium solution down here at y equals negative pi, and so on. Let me label our axes. This is t, this is y. Whew, that's kind of cool. And we can answer more things, right? When is the slope positive? All right, when is the slope of y positive? Well, again, exponential functions are always positive. They're never 0. Trig is between -1 and 1, but it's getting squared, right? This thing right here is always 0 or positive. So it's actually positive everywhere except when it's 0. So it's everywhere except when y equals pi k. Everywhere except these green lines, this function's increasing. And watch this. I'm going to ask you one more question, one more thing that we can analyze without finding any analytic solutions at all. We're just looking and what do we know about these functions? So in each piece, I'll talk more about what that means later. When is the slope the biggest? And when I say each piece, right, it's these equilibrium solutions are repeating. Right? Sine is periodic. So there's some level of periodicity in each of these chunks that's getting scaled. So it's getting bigger as y increases. It's getting smaller as y decreases. There's some level of periodicity. But the biggest, right, in each chunk is roughly going to happen when, like, I don't know, the sine's periodic, right? Sine is 0 here and 0 here. It's going to be the biggest somewhere in between. we can use all that information to say like, okay, well, what's kind of happening is the slope is close to zero at all these close to all these green lines. It's always increasing. And then it's biggest kind of in between each green line. It's getting close to zero at the green lines because those were the equilibrium solutions. Equilibrium solutions were when the slope is zero. Slope is zero at these green lines. And we have this idea of what all these solutions might look like. Also, we know it's autonomous, right? We know there's no time component to this differential equation. And what we said in the previous video is if we know something's autonomous, then if we have one kind of solution, we can get infinitely many versions of that by shifting it to the left and the right. So if I think it's going to look like this, well, we can also have a solution that looks like this and a solution that looks like this. A bunch of vertical solutions or horizontal translations of solutions. All right. And now, all of a sudden, we have something super hard. This is a complicated function. I can't graph this function by hand either. I can't really plug in that many values of this function and know what they are. It's really complicated. I don't need to plug in anything. I don't even need a precise slope field. But I can analyze some basics. What are equilibrium solutions? When are things positive? When are things negative? When are things the biggest in each chunk? And all of a sudden, I have a picture of what the solution looks like. And if you know anything about differential equations, just looking at this equation and the idea that you could possibly have any picture of what the answer looks like is insane. But after asking 3 questions, we know what these solutions look like. And now there's still some uncertainties, right? Like we don't know whether these green lines are asymptotes or they could be like cubic functions, right? Where they get really close and then cross, right? So we don't know which situation it is, right? Is it an asymptote or does it just get tangential and then cross? We don't know the answer to that from this qualitative analysis. Okay. But we have a pretty good idea of what's happening, which is pretty cool. So I think those are the main things. Now, I'm sure all of you want to know what's really going on. So let's use our tools. Let's use technology. Let's get the answer over here. Okay, so we're going to look. I'm actually going to set up the slope. Let's go from, let's see, kind of like we were doing before. Yeah, maybe 2 pi to 2 pi is actually still good. And then the, oh, no, that's what we want for the y values, negative 2 pi to 2 pi. And then for the x values, I don't really know what I want for the x values. We'll change these x values later for our viewing window. Let's type in our differential equation. We are using y's here. So let's say, all right, that was e raised to the y squared over 10 times sine of y squared. And lo and behold, what do we have? Let me clear these curves. You can again see, oh, look, we have all of those horizontal translations within each piece. We have all those equilibrium solutions that we can see, right? These are the equilibrium solutions. There's the horizontal translations. And again, it repeats. And now notice something as well, right? Remember when I said that, oh yeah, it basically repeats, but it gets steeper as y increases. You can really see the steepness happening because this is an exponential function. This part's periodic, which is why we have these periodic equilibrium solutions, but this really is scaling it steeper. And now we have an idea, and again, I don't have a perfect picture here, but honestly, that's pretty similar, right? With very minimal math, which is extremely powerful. And I could go on about this for a long time, as you can tell, but it's very cool. But that's the power of qualitative analysis. Remember, we have these 3 pillars of this class for analysis. Analytic solutions, solve by hand. Qualitative solutions or qualitative analysis is something like this. It involves slope fields a lot of times. And then also numerical analysis, where we get approximations with computer programs, and we'll give an example of that in the next section. Not the next video, the next section. Okay? That's the basics of this section. We close section 1.3 with an example of an RC circuit. So we'll do some more analysis with a more hands-on example in the next video. So stay tuned and hope you're enjoying this. Oh, and we'll have October say goodbye. She's still sleeping. Okay. Bye-bye.